very nice workshop, conference. And I apologize in advance because I don't have anything related to the word semi-infinite or critical level. And in fact, it's mostly physics talk. But anyway, so I'm going to talk about some applications of, well, I think new applications of topological field theory, or fairly new applications of topological field theory. And in particular, I'll explain, well, I'll review some old topological field theories known as Digraph-Witten theories. And I'll review what they're good for. And then that special kind of gauge theory is based on finite groups, and therefore pretty simple. And then I'll explain that there are interesting generalizations based on two groups, and then I'll explain what those are presumably good for. And these are papers which are on the archive. So in particular, I'd like to pay attention to Ryan Thorngren, who is a first-year graduate student now in Berkeley. And well, since the paper is already on the archive, he was an undergraduate when we collaborated on this. It's pretty impressive for an undergraduate. So, okay, so first of all, what are these phases of matter, which you saw in the title? Well, if it were a physics conference, I wouldn't explain this, but since it's a mostly math conference, I have to explain what a phase is. So what are phases? But phases, well, when people talk about phases, they usually mean, well, say, okay, gas, liquid, solid, plasma, whatever, the stuff you learn in well, depending on where you come from, in 6th or 7th or 8th or 9th grade in high school. Now, I don't mean these phases specifically, but I meant something slightly different, namely phases of quantum phases, namely things which happen at 0 temperature. Well, a good example of such a phase, less familiar, it's not studied when discussed in high school. Liquid helium so it's a quantum liquid that exists at 0 temperature. Or you can have like electron liquid in metals. Ferromagnets, when it's a piece of material where all the spins of electrons are aligned. Another familiar example. An insulator. No. These are just phases of matter, not yet gapless, not yet gapped. Let me just finish. Well, I'm explaining what phases are, and I'm going to explain what gapped is. Okay, so then super insulators, very boring things, they don't conduct anything. Well, superconductors, ideal conductors, all kinds of examples. Well, QCD vacuum. So now what is a gapped phase? Well, gap refers to the spectrum of the Hamiltonian. So if you look at this finite piece of this material, well, the Hamiltonian, of course, has a discrete spectrum, always has a discrete spectrum in finite volume, but the question is, as you take the volume to infinity, if you take a very large piece of this material, is the distance between the lowest level and the next one, does it remain finite or goes to 0? If it remains finite, this difference is called a gap, and people say it's a gapped phase. Now, most familiar phases are actually gapless, like say liquid helium or electron liquid, ferromagnets. These examples of gapless phases. That means that they're excited. Well, if you take if the piece of material is very large, the lowest sort of excited state is separated by a very tiny amount from the ground state. And that's because these phases have to do with, well, they're characterized by something called spontaneous symmetry breaking. But there are less familiar phases, like actually insulator or superconductor or QCD vacuum are less familiar, and they're gapped phases. And they're, well, okay. And they seem a bit less interesting, but actually people recently discovered they can also be quite interesting. In particular, insulators, actually many different kinds of insulators, not just the boring statement that something doesn't conduct electricity and that's it. Okay. Now, what does to do with quantum field theory? Well, first of all, what is topological field theory? Also, it's a field theory which is invariant on the infinitesimal diffeomorphisms of spacetime. That is, well, in particular, doesn't depend on the metric. And the lore is, I'm not going to try to argue this, but is that any gapped phase of a quantum system at long distances or low energies, it becomes is described by topological quantum field theories. So the gap here is quite, yeah, well, or inverse mass. So the mass gap is an energy scale. You take the inverse of that, then you get some distance scale, and at much long distance, you get this topological field theory description. Now, whether that's not a theorem by any means, but in particular, topological quantum field theory, well, it has a huge invariance. In particular, it's Lorentz invariant, while the phases we're studying don't have any like Lorentz invariance or anything like that, but they're not relativistic. But nevertheless, it's believed to be true. Now we're going to use topological field theories to classify possible phases. And I'm going to describe, well, question then arises, well, can you classify all topological field theories? Well, that's probably impossible, but we can describe a large class of them. Well, the most boring case is an ordinary superconductor, what's called BCS superconductor, described at long distances by gauge theory with a discrete gauge group, Z mod 2. It's Z mod 2 because electrons are in pairs. So there's a condensate of electron pairs called Cooper pairs. And so that's why it's Z2. Like if electrons would combine into triplets, you would have Z3 gauge theory. Okay. Now, well, actually, this topological field theory can be used to characterize the gapped phase, but it's often trivial. Like for ordinary insulators, for example, it's trivial, nothing happens. However, more recently, people discovered, for example, there are insulators with a non-trivial topological field theory describing the long-distance limit, and they're called topological insulators. And there are also more interesting superconductors called topological superconductors. So that's the motivation to study topological field theory and try to understand how many there are and what sort of phases they describe. Now, suppose you do know what topological field theory, well, what is it good for? Well, first of all, it describes some of the correlators, some of the observables, namely those which do not decay exponentially at long distances. Sorry? So the Hilbert space of the theory of this topological field theory is a space of ground state, that is zero energy states. More precisely, you have a finite piece of material. The states don't have exactly zero energy. They slightly degeneracy, but this difference in energies, there's some several energy eigenvalues which are close to each other, exponentially close to each other as you take the volume to be large. And in the infinite of large volume, they become exactly degenerate. And those are the quantum states that topological field theory sees. And then there's a gap, and there's lots of other states, and topological field theory doesn't describe those. So that's item 2. Topological field theory can tell you how many almost degenerate states you have, or almost zero energy states you have a compact space. And finally, topological field theory is useful to describe the boundary behavior. Like these topological insulators, for example, they're characterized by the fact, well, in particular, by the fact that on the boundary, typically there is conductance. There's no conductance on the bulk, but on the boundary, current can flow. So, topological field theory should be able to describe that. So what are possible phases and what are, let's focus on gauge theories. So there's Yang-Mills theories when one of the fields is a connection on some G bundle. Well, first, the most familiar case of a non-trivial phase of a gauge theory is a Higgs phase. And where this is sort of condensate of electrically charged particles. Well, superconductor is like that. Standard model is like that. Well, in gauge theory, one has some microscopic gauge group, but when some particles condense, then they break the gauge group down to a subgroup. So this is a subgroup which is called G, which is a subgroup of G naught. So Higgs phase is partially characterized by this unbroken gauge group. So, and the law of energy physics is described by a gauge theory with this gauge group G. Now I'm going to explain this, but if you want to get a gapped phase, G has to be finite. So, for example, in superconductor, G naught is just U1, the circle, and G is Z mod 2, so which is subgroup of U1. And that's why superconductor is gapped, because unbroken group is finite. Now, these theories are very simple, because summing, you have a path integral formulation as usual of this topological field theory. Well, when you have a, it has some Lie group in general, And G in general is some Lie group. And if it has non-trivial Lie algebra, then you have like photons, as many photons as the dimension of this Lie algebra. So the Lie algebra, well, if you don't want to have any massless photons, naively at least, you want to have the Lie algebra to be trivial. But when Yang-Mills fields were first discovered, like Pauli was present in the first seminar where we discussed, and he asked, okay, can you have a mass for this photons? And when the answer was no, he basically left the room, right? Because at that time, no massless photon. Well, there's only one photon known, and no extra ones. So he said it's unphysical. Now later, people discovered this confinement mechanism, which is something different from the Higgs. So you can have different ways to make your photons massive. One is to break the gauge group. Another one is to use this confinement, like condensation of magnetically charged particles, if you wish. But I'm going to discuss something related to this later. But for now, if you just have Higgs effect, if the gauge group is broken down to a smaller group with a non-trivial Lie algebra, then you're going to have massless particles. So you're not going to have a gap. So that's why you need to have a finite group. And once you look at the effective description, just have your path integral, your Feynman path integral becomes a sum over G connection, which is essentially the same as sum over G bundles. Now, it doesn't mean that the theory is completely boring. There is some interesting extra data you need to specify, because when you sum over G bundles, you should assign some weight to each G connection, and there's more than one possible way to do that. And this is precisely the problem which Dagger and Witten addressed in 1990, and they showed that you can consistent assignment of weights is, there's one such consistent assignment for every, if you're in D dimensions, D space-time dimensions, then the possible choices of these weights are labeled by elements of this cohomology group, or the classifying space of G, degree D cohomology group. So let me review those theories. So first of all, for every group G, we have some classifying space. We're interested in the case when G is finite, and then in that case, G is the this classifying space is characterized by the fact that pi1 is G and higher homotopy groups are trivial. So it's an Ellenberg-MacLane space. Like, for example, for Z2, which is the most sort of physically interesting example, it's RP infinity. And there's some universal G bundle over BG, and any G bundle can be obtained by pulling back this universal G bundle. So you can think about summation over G bundles on your manifold X is the same as summing over homotopy classes of maps to BG. So gauge theory for a finite gauge group is very much like sigma model with target BG. So, and the action is pullback, must be, when Dagger and Witten explained this, and then they said, well, what is the possible action? Well, the action should be some pullback of some, have some map, phi, from your space X to BG, and then to get a local action, you just need to get some top degree form on your X. How can you get it? Well, you just pull back some form or some degree D cohomology class on BG. So that's all there is to it. So, and then you integrate. So that's why actions are labeled by choices of this cohomology class. Now, by the way, people often denote this cohomology group, it's group cohomology and denote it like this. I'm not going to use this notation because later I'll also make use of iterated classifying space, which makes sense if the group is abelian. So if your group is abelian, you can iterate this classifying space construction, so let's say B squared G is the same as is an Ellenberg-MacLane space KG2, for example, and B's cube is Ellenberg-MacLane KG3 and so forth.
So how do you integrate a function with values in U1?
Well, okay, when I say U1, I really meant like R mod Z, R mod integers. So I have a cohomology class which I integrate over, I evaluate on the fundamental class of my manifold.
Because you don't really need, you only need action up to
Yes, so when I say, I usually, sometimes I just want to distinguish U1 and R mod Z when they're related by the exponential. So the action is an element in R mod Z, then to get a number, I multiply by 2 pi I and exponentiate. So this number is the weight, so this exponential of the weight of the actions for me is basically the same as the action itself.
So the coupling constant will be an int?
The coupling constant is actually this cohomology class. So if you wish, it's, okay, so, for later use, we're also sometimes going to use not just cohomology with coefficients in U1, the trivial module, but also in some other module. You have some, say, abelian group A on which G acts. You also have cohomology in some local system with fiber A. And well, I'm going to do it like this without indicating exactly how G acts on A. So it will be clear from the context what the action is. Now, well, the way diagram had written presented this, well, in a less abstract way, they presented it very concretely. Namely, so cohomology class is some function of D variables taking values in G. So a cocycle is some function with variables, and cocycle condition is some linear constraint on this. So for example, for D equals 2, you have this constraint. And you have cohomology, some cohomologous, well, relation will be cohomologous, like here's an example in dimension 2, where it needs to be cohomologous. And once you have this, okay, so how do you actually construct this field theory? So concretely, not like the way physicists like to do it. Well, the way it works, well, first, if you just assume that X has a triangulation, later one can argue that nothing depends on triangulation, one can describe it as follows. So we pick a triangulation, and let's also pick some ordering of vertices. And so what is the configuration of a space over which we sum? Well, it's a space of all flat connections, modular, some gauge transformations. Well, actually, it's just an example, but this part is true in any dimensions. Yeah? Well, one can use something, one can have some so-called branching structure, like something which is an ordering locally. Just to assign, well, I need to, well, later I'll need it. In high dimensions, for sure I need it. So
when you take, so you compute some things with values in Q1, but then when you take a sum, you interpret Q1 as sitting inside of the complex equation, yes?
Oh, well, each configuration, so first of all, there's a configuration space, some set. And for each element of the set is an assignment. Let me explain the configuration space. Then I'm going to say how to sum over them. So first, what is the set you're summing over? Set of configurations is the following. So for each edge of the triangulation, you have a group element. For each two simplex, you have a constraint like this. And that's our configuration space. You have a D, so suppose in D dimensions now. Even though in D dimensions, all the data live on one simplices, and the constraints are only on two simplices. Now, what is the weight? Well, the weight of a configuration is the sum over all D simplices, because you're in D dimensions, right? So you're supposed to integrate, the fundamental class is the sum over all D simplices. Each D simplex contributes this, where I think of this as taking values in integers, in real modular integers. So then multiply by 2 pi I, and then get something which can exponentiate and get a complex number with absolute value 1. Then just sum over all possible configurations. That's what the path integral is in this case. So the whole construction is very much like lattice gauge theory, if you know what it is, but if you don't know, it doesn't matter. But anyway, the point is that there is a constraint. In the usual formulation of lattice gauge theory, the kind of physicists use, you just have an assignment of a group element every one simplex. There's no constraint. But here there's a constraint for every two simplex, but one doesn't have to be, well, one can enforce it using some Lagrange multiplier or something like that. So it's not an essential difference. And the action of this sort is invariant under G gauge transformations, and the G gauge transformation is a G-valued function of zero simplices. So if you don't have a closed manifold, then the action actually is not invariant. There's some boundary term in the variation. Well, that's a tricky thing. So it turns out that if you have a boundary, if the class is non-trivial, there's no way to maintain gauge invariance on the boundary. You have to break it. It has to do with some sort of anomaly, if you wish, gauge anomaly. So this theory is for non-trivial class. Do not admit, well, you have to break the gauge symmetry on the boundary. Well, the action won't be gauge invariant unless a restriction, well, this is non-trivial, so it's not a co-boundary of anything. If it were a co-boundary, you could sort of cancel variation by choosing an action to be that D-1 dimensional cycle, but it isn't. It's not going to help you. Well, you can do it. You can do it, but yeah, but if you have a non-empty boundary, in this cohomology class is non-trivial, the action will not be gauge invariant. So it's a sort of anomaly. It's like you cannot do it with finite, within this class of field theories, which is finite a set living on simplices or zero simplices. You cannot cancel this anomaly. So that's basically what means class is non-trivial. Well, sometimes these theories are very boring. Like if you look at even dimensions and the typical physical cases, like when the group is Z mod n, very typical, like Z mod 2, for example, that actually is trivial. So then no interesting diagram theories in, say, in 4 dimensions. But in, say, 3 dimensions or in any odd dimensions are interesting theories, and they're essentially like Chern-Simons theories in the abelian case. Now, in 2 dimensions is some other interesting case where, if you look at products with cyclic groups, then this is a non-trivial action possible, and that has to do with this discrete torsion on orbitals. Now, as you can see from the definition, diagram theory is, since it's basically a sum over G connections, where G is a finite group, the only thing it cares about is the fundamental group of the manifold. It's very, doesn't care about anything about what higher homotopy groups are. So you want to construct some more interesting topological field theory, which actually does care about higher homotopy groups. You need clearly some gauge fields which are sort of p-forms, or which care about high-dimensional cycles. Now, in general, we can have p-forms all the way up to the dimension of the manifold, but let's restrict to 1 and 2. We already have these fields living on 1 simplices. Let's also add fields which live on 2 simplices.
But didn't you took a pullback of the class and integrate over X?
Yeah.
Couple it with the fundamental class of X.
Yes.
So it cares about homology of X also.
Well, the configuration space only, yeah, okay. So in that sense, yes, but configuration space only cares about pi 1. So, okay, I don't know. It just works. So I want to generalize it so that the configuration space itself is sensitive to higher homotopy groups. So the question is what's a consistent way to do that? So if I have fields which live both on 1 simplices and 2 simplices, then presumably my gauge transformation live on both 0 simplices and 1 simplices. And so what sort of structure describes all this stuff? Now, natural guess is that, well, if the starting point for diagram theory or gauge theory in general is a group, then once you have higher form fields, then you need to deal with the, say, P group or D group, well, in this case, 2 group. So let me explain what a 2 group is. Well, the way I think about groups is just, it's good to think of it as a category with one object and all invertible morphisms. And physically, morphism or arrows describe symmetry transformation. So
for every space-time X of dimension, so if you fix the group G,
yeah.
for any X, you get a number.
Yes.
Which is a sum over all G connections of X.
Yes.
Some integral over X. Pullback of this one.
Yes.
And so you're saying that if you have 2 manifolds of the same dimension, which have the same pi 1, you will get the same number?
No, I don't think.
Well, I mean, you use the fundamental class of X.
Yeah, I guess it depends on more than pi 1. But nevertheless, yeah, so I'm going to introduce these higher form fields, just so in configuration space is sensitive to the homotopy groups. So, okay, yeah, right. Yeah, but you're right that the action itself is an integral of fundamental class. So, what's going to be a symmetry? Well, a symmetry in dimension, one can argue that a symmetry, in general, when dealing with a symmetry in dimension greater than 1, then, like in any quantum theory, you should think about the symmetry being really, involving not just arrows, but arrows within arrows and so forth. So, for example, well, I'm going to skip the motivation, but anyway, so if you only have arrows and arrows between arrows, then they're described by a two group of symmetries. So it's a two category with one object and invertible arrows and two arrows. It's a special kind of tensor category. I don't want to work with this abstract description. So there are two other more convenient descriptions. I was explaining that in the previous transparency, in the previous transparency, I essentially explained why I expect high categories to arise as sort of symmetries, and namely because when you have a group element, when you have a symmetry, you have a codimension one sort of defect in your d-dimensional space, right? But when you have, why can't you also can have codimension two defects and so forth? Like in quantum mechanics, if you only care about time, you only have codimension one things and nothing else. But in dimension higher than one, higher dimension defects. If you think about what sort of structure they form in d dimension, they form a D category. Okay.
You can think of it as a monoidal category where every object and every morphism is invertible. This is what this has to do.
Yeah. Okay. Okay. I'll explain in a second. Okay, but anyway.
You can realize it by light cross model, which is the next.
Yeah, which is the next slide. So there are a couple of different ways to describe them, like purely group theoretical. Forget about all these categories and two categories. So we can describe it, for example, like this. You have a pair of groups, homomorphism from H to G, and an action of G on H. And that's a couple of conditions. Now, well, that turns out to be equivalent to this definition using a two category with invertible objects and with invertible arrows and morphism, two morphisms. Namely, G is a set of objects, or a set of arrows in this two category. And H is a set of two morphisms from the identity morphism to any other morphism. Okay.
But G and H are not mutually determined.
Yeah, that's true.
Because equivalent categories maybe not isomorphic.
Yeah, that's on the next slide. So this thing is called a crossed module, this gadget. And it was introduced by Whitehead, and because that describes, say, the relation between first and second relative homotopy groups. Now, physically, this two group itself is not a well-defined thing as a set. Namely, two groups can be equivalent but not isomorphic. So there's some physical interpretation of this fact. I'll discuss it later. But one can, instead of working with, there's another way to describe this two group, which is sort of more invariant. So sort of choose a minimal model, and which obtained by sort of passing to a skeleton of this monoidal category. So it identify isomorphic one arrows. And you get the following smaller piece of data. You have, first of all, pi1, which is a co-kernel of this map T. You have and this is just a group. Well, it's a group. Then you have a abelian group, which is a kernel of T. And then you have action of pi1 and pi2. No, it's good. Action of pi1 and pi2. And then cohomology class here, as well as obvious invariant here. In the topological interpretation, this is to do with this data, this G and H and T and alpha describe some two homotopy type of your space, and then this data describe, this is basically Postnikov class here. Okay.
So you can think that the object of your monoidal category is elements of phi 1, and
yeah.
morphisms from any object is phi 2, and then
Yeah, and this is associator. Yeah. Pi 1 is non-abelian. Pi 2 is also abelian. Yeah, well, there's those two properties ensure that the image is always normal.
and the kernel is centered.
Yeah. So, okay, so this is the basic datum which replaces the notion of a group. So in digraph-Witten theory, there was a finite group, and here we're going to have a finite two group. What I mean by finite two group is that this minimal model is finite. This G and H don't have particular significance, but this pi1 and pi2 should be finite. So, and then there's notion of two connection for this for a two group, I'll directly jump by, well, if I triangulate my manifold, I can describe a two connection very explicitly. So what is this? Well, this is going to be just minimal model description. One can also use the other description with G and H, but I prefer this one. So I have a group pi1, which is finite. I have an abelian group pi2, an action alpha of pi1 and pi2, and then this class here. Now what's the configuration? So I'm going to describe first configurations, which I'm going to sum over, and then I'm going to explain how to compute the, well, what possible weights one can have. Well, first of all, well, in the digraphic description, those are the only, a G connection described by one cocycle with values in the group G. Here we're going to have we're going to have still a one cocycle with values in pi1, and also going to have a two cochain with values in pi2. So A is still a cocycle. B is not a cocycle. This is sort of twisted cocycle constraint, which I'm going to explain in this, here. So the way I label, well, I have this ordering of my vertices. So the way I label my, B's live on faces of this tetrahedron. And the way I label them is that the phase opposite to 0 are called B0, and the phase opposite to 1 is called B1, and so forth. And I also label this edge variables A0, A1, A2. They're like A0 is from 1 to 0, A1 is 2 to 1, and A2 is from 3 to 2. That's why I need ordering to make this well defined. And then, all others, as before, once I specify this one simplex variables, all the rest are fixed by the constraint, the cocycle constraint on my one cochain. The B's, on the other hand, satisfy this twisted constraint. Like if I didn't have the right-hand side, if I had 0 there instead of this beta, it simply would say that B is a two cochain with local coefficients, two cocycle with local coefficients. That is pi1 acts on pi2, and this is vanishing over this would say that this is a closed, twisted two cochain. But actually, this is defect coming from this class beta. Now, these constraints are invariant under these symmetries, and symmetries live. There are two kinds of symmetry transformations: the one which lives on 0 simplices, and the one which lives on 1 simplices. And they take values in pi1 and pi2 respectively. Now, shorthand for this is just, A is a one cocycle, and B is a twisted two cocycle. And here I'm thinking about beta as a cohomology class in BG, and A is a map to B pi1, and A is a map to B pi1. Okay, this describes the configuration space of my sort of lattice model. There's some symmetries there. I explain here what the symmetries are. Well, they're sort of one-form symmetries described by pi2 valued functions on one simplices, and then there are also zero-form gauge transformations. And the difference compared to the previous case, now there are gauge transformations between gauge transformations. The gauge symmetries themselves have gauge symmetries. So when you do the digraphic theory, you sum overall configuration, then divide by the order of the gauge group. Here you do the following. You sum overall configurations, divide by the order of the gauge group, but then you sort of overcount it because some gauge transformations actually themselves relate, then multiply them by the order of the group of gauge transformation between gauge transformations. Okay, that's my next transparency. Yeah. Okay. So again, so one can classify actions. So one can think about this two connection again as a maximal classifying space of a two group. This classifying space is some vibration of one Edinburgh-MacLane space over another one. So and again, the action is a integral or pullback of this classifying of this class. Now, if I actually write out what it means to have that is a description of this cohomology of the classifying space of a two group, very explicit description, just like we had the classifying like group cohomology has very explicit construction in this bar construction and very explicit condition, but when you try to apply it to two groups, well, you can write it out, but it's so complicated, it becomes totally useless. Nothing you can compute in this way. Like, for example, for, well, a decode chain, for example, for this two group is a function of d variables in pi 1 and d times dimension on two variables in pi 2. It's a horrible thing, even in low dimensions. There's no way to solve it. Now, but in low dimensions, one can use Serre spectral sequence to understand cohomology of BG for this classifying space. Now, you have trivial pi 1. Curly G is this two group. It's a two group. So it has either have this minimal model or have pi 1, pi 2, alpha in the cohomology class. Yeah. Yeah, it's a two group. Or you have this G. Well, it's an Eilenberg-MacLane space of pi 2 fibered or Eilenberg-MacLane space of pi 1. So it's one of the. Okay. So, well, if you have trivial pi 1, then just have Eilenberg-MacLane space, k pi 2, comma 2. So that's written here. And then one can compute cohomology in all degrees, even, that was actually before Serre applied his spectral sequence to this computation in 1954. And this is a nice paper of Eilenberg-MacLane, which does this. Like in low degrees, one gets, for example, the most interesting, the first interesting case is actually degree 4 cohomology. Space of quadratic functions on pi 2 with values in U1. Now, if you want to know cohomology for general pi 1 and pi 2, that becomes tricky. So let me explain. Well, we only looked at degrees 2, 3, and dimension 2, 3, and 4. Well, this class beta, wedging with it defines a map like this, and maps rather for all k 0, 1, 2, 3, and so forth. So in degree 2, this cohomology is simply just kernel this map. That is, it's an alpha invariant character of pi 2, which is also annihilated by this class beta. So it's a pretty simple condition. If you go to higher degrees, well, in high dimensions, it gets more complicated.
Is this class a direct sum?
I think it's direct sum, but this isomorphism is not canonical. So.
Are these direct sums with the spectral sequence gives at AE infinity?
Yes.
Then maybe you have an extension.
Well, I don't think you have actually, but I think there's no canonical splitting. I think, but I think they split actually.
Because what the spectral sequence gives you is a gradient.
Yeah. But well, okay. I have some doubt. I'm not quite sure about d equals 4. I'm not sure we showed it, but in dimension 3, definitely splits. In dimension 4, there's some slight confusion there. So, but anyway, so okay. So this was a description of the model, and it's completely explicit. And one can, compute, the partition function or compute correlators on observables. Well, if interested, there are different kinds of observables. Like if you look at 4 dimensions, then there are 2 kinds of sort of observables, living on sort of loops, like Wilson loops and Hooft loops, if you wish, labeled by elements of pi 2 and representations of pi 1. And then there are 2 kinds of surface observables, that is living on 2-dimensional surfaces in your 4-dimensional manifold. So I want to conclude by explaining the physical application of this field theories. There are actually 3 physical applications, but I'm going to describe one of them to take us too far afield. Now, first application is the classification of gauge theories. So this is explained when you have just Higgs mechanism, which breaks your some Lie group down to a finite subgroup. You have this Zagreb-Witten theory, which describes the long distance limit of this field theory. Now, there's another mechanism to sort of kill photons, and that's confinement, or condensation of magnetically charged things. So the question is, what sort of topological field theory describes a situation when you have both Higgs effect and confinement? And that's a conjectural answer, actually. Well, we don't know if it's correct, but there's some arguments which show in special cases it's correct, and then we sort of boldly generalize what we saw there. Namely, that this 2-group topological field theory describes the most general phase of gauge theories, which is gapped and comes from Higgs effects and confinement of some microscopic gauge group. And that sort of explains why this G and H weren't sort of canonically defined, why different two groups with different G and H can carry the same sort of physical information. So G is interpreted as a subgroup of the microscopic gauge group, which is not Higgs. Now, imagine this picture. So first, some microscopic scale, the gauge group G is Higgs to some subgroup, and that says G. But then at long distances, some confinement turns on and confines part of this gauge group, and that's why G is not really visible at long distances. What's visible is the co-kernel of this map T, which is the effective long-distance gauge group, and also the kernel of T, which labels magnetic fluxes of this set Hooft loops. So that's one possible application of this topological field theories. Another one has to do with solid-state physics. So recently, notion of a symmetry-protected topological phase became very popular. So what is this thing? Well, it's not a, okay, this is a bit, G means something different here. Suppose you just have symmetry G. And it's a symmetry, not a gauge symmetry, it's a global symmetry of a problem. Like maybe you have a lattice model where on each side you have some, each zero simplex you have something which has a symmetry G. So that's usually called on-site symmetry. So these G transformations act on degrees of freedom at every site separately. Now, imagine I have this phase is gapped at long distances, and then we want to classify all such phases modulo up to homotopy, so the deformations of the Hamiltonian or the action which preserve all these properties. That is, we don't allow anything which breaks the symmetry G, and also do not allow the system to become gapless. So we want to preserve the gap and the symmetry. So how many such phases are there? Well, for example, one example is an insulator. So an insulator, by definition, has a symmetry U1, which is a conservation, well, has to do with conservation of electric charge, and may also have time reversal symmetry. So in that case, this G would be either U1 or U1 times Z2, where Z2 is time reversal. So we want to classify such phases which are gapped and have this fixed symmetry. Now, turns out that there are indeed non-trivial homotopy classes, and this homotopy class is called symmetry-protected topological phases with symmetry G. Now, the outstanding problem is to classify symmetry-protected topological phases with a fixed symmetry G. How many are there? Now, one way to, well, we don't really know the full classification, but one way to find invariance of these homotopy classes is to promote the following. You promote the symmetry to a gauge symmetry. Basically, your G transformations is originally just a constant zero cochain, and then you make it it's a closed zero cochain originally, but then you make it to be non-closed zero cochain. So physically, it means that you somehow couple your system to a flat gauge field for this group G. Now the system is gapped, so once you integrate out everything except this gauge field, you're going to get some function for this gauge field, which is sort of effective action for this gauge field, which describes a topological field theory of some sort. So to every symmetry protected topological phase, you can assign this topological field theory with gauge group G. And therefore, you can assign this element here. So that doesn't completely characterize all the phases, but it's a nice start. So if you can label your phases by these cohomology classes. So the most simplest case is when G is finite. By the way, in the case when G is not finite, this logic also applies, but then one has to study the classifying space for flat G connections, not for general G connections. So BG, when G is a Lie group, BG is different from BG discrete. And actually, cohomology of this classifying space is not known as far as I know. Now, if you only look at measurable cochain for this classifying space, then I think it's known. Sorry? Well, if you look at measurable cochain, they're actually quite fairly small. But I think nobody knows what this is. What cohomology is for general cochains. Maybe there's some physical reason why you should only look at measurable ones. Actually, I think it's physically only the measurable ones are important. Okay, so now I'm going to try to generalize this. So far we consider just symmetries which sort of live on every side separately, and then promote it, make this, so that symmetries labeled by 0 cochains. Now we can also have maybe symmetries labeled by 1 cochains. And then when you gauge that, you're supposed to, when you gauge a normal symmetry, which acts on sides of your lattice system, then you need to introduce a gauge field. That is a gauge field for the symmetry. But when you gauge this sort of one-form symmetry, you need to introduce a two-form gauge field, which lives on 2 simplices. So that's actually, so once you integrate out everything, you get some effective action for this two-form gauge field, which lives on 2 simplices. And as I explained before, these actions are labeled by this cohomology group. So that's a bit different classification. Well, so different kind of symmetries then. There are on-site symmetry, there are like edge symmetries, and there's a different classification of different, the group itself doesn't really tell you the whole story. There's also the question of what it acts on sides or on edges. So this gives a generalization of this previous class of symmetry protected topological phases. Now, when we have both G and H non-trivial, or both pi1 and pi2 non-trivial, presumably that leaves even we have both symmetries living on 0 simplices and 1 simplices, and presumably even more symmetry protected phases appears. But I'm not sure physically what this, there's some confusion about, at least in my mind, how what it means to have for a general 2 symmetry, general 2 group to be a symmetry of some particular lattice model. Now, in principle, there's no reason to stop with 2 groups. I mean, we have lattice model in D dimensions. You can have symmetries living on simplices of all dimensions up to D. So then you need a D group. But that gets complicated. And last remark is that if you just forget about this problem of classifying SPT phases, just look at this gauge theories for 2 groups, you can ask, okay, maybe, they look different because they involve both sort of 1-form and 2-form fields, gauge fields. But maybe there's some duality which relates them to more familiar theories, like two-digraph-Witten theories. And indeed, in some cases, in a paper with Ryan, we showed that there's some duality transformation, which can be performed in lattice, which relates some of these theories to digraph-Witten theories, or some modest generalization of digraph-Witten theories. But in general, it's not possible to do this. So, like in particular, this class here, is non-trivial. There's no way to dualize to digraph-Witten theory. Okay, I'll stop here. You should ask someone else about this. Don't ask about high K theory. I have no idea what this is. No, I didn't. I can't consider this possibility because I don't know anything about higher K theory.
One more question, sorry, just one more question. Why don't consider just the extension of H by G? Because of spectral sequence, many of your cohomologies can be understood in terms of one guy, which is just extension, right?
Degree 2 cohomology. Well, H is not abelian in general. H is not abelian in general.
But G is not abelian, H is abelian.
No.
Only the kernel.
The kernel is abelian, yeah.
What you're discussing is some proportions of spectral sequences.
Crossed module is a 2-step extension. It's a double extension, if you wish.
Yeah.
How would you deal with combination-free defects?
Sorry.
Combination-free defects, can they be dealt with?
Well, I said that in 4 dimensions, there are loops, so there could dimension 3 defects in 4 dimensions. So, so some of this, these field theories have some defects of fixed dimension, fixed codimension. So depending on dimension, you can get codimension 3. Like in 4 dimensions, there are codimension 3 defects.
Can I? So using this approach, given a group G or maybe a 2 group, which is finite, and d-dimensional manifold X, you get some number, right?
Okay.
And so you get some invariance. So if you fix the group, you get some invariance of manifolds.
Yes.
Yes? Can you give an example of what kind of invariance you get in this way?
Well,
Maybe
like in the case of when you just have this pi 2 and pi 1 is trivial, so essentially you get the signature of the manifold. The partition function detects the signature. Oh, and for a four-dimensional case. We'll look at four-dimensional case and take trivial pi 1 and non-trivial pi 2. Then you have just the action is quadratic function pi 2. And the partition function is basically the signature of this quadratic function times signature of the manifold divided by 8 exponentially, something like that. So in that case, it takes signature. In general, well, for both pi 1 and pi 2 non-trivial, something complicated. I can't really describe.
Do you have a definition of a D group for general D?
Yeah, D category with the one object and no invertible morphism, two morphism up to all the way.
I mean in the sense of a 2 group in the same manner. So as a pair or
Well, that's the same thing. If you want to make it explicit, you need to know definition of a D category. So. Yeah, that's a good way of putting it. Yeah, so that's sort of data.
Anybody else? Okay, let's thank the speaker again.